Hello everyone, welcome to my channel. I hope this channel will be helpful for those students who are preparing for NEET, IIT-JEE, KCET exams. So in this series, I'll try to explain some key concepts that are required for these exams while solving MCQs. I'll pick up previous year MCQs. While solving those, let's look into the concepts which are involved behind those questions and also how to solve it. I'll try to explain the concepts to the best of my knowledge and ability. I also request all the students to try as many sample problems as possible so that you can gain more clarity in the topics and also increase the speed with which you are solving them. So the speed is an important factor when it comes to your final exam. You can contact me in case you have any doubts. So without any ado, let's start with the first topic which we are going to talk, that is chemical kinetics. It's one of the important topic under chemistry. So before going to the MCQs, I would like to discuss some important concepts in this particular chapter. I'm not doing the derivations, I'm just writing the direct equations. Derivations I will explain in another video. If you require any clarity about anything which is mentioned in this video or otherwise in your textbooks, you can leave a comment, and also please subscribe for notifications on my further videos. So let's start. So chemical kinetics, it deals with the speed of the reaction. So reactions can be slow, moderate or fast, but what speed is it happening at, and how do we find out? We measure the change which is happening in the concentration of reactants or the change which is happening in the concentration of products with the time. This is the rate of our reaction. So this is the rate of our reaction. Here the concentration of change in concentration of reactants is the concentration of reactants final minus the concentration of reactants initial. For any reaction, the initial concentration of reactants will be higher compared to the final concentration of reactants, which makes this negative. So ultimately we are going to get a negative value for the change in the concentration of reactants. So for products, this is going to be the change in the concentration of product is going to be the concentration of products final, which will be higher than the initial concentration of products, which gives us a positive value for the concentration of products, change in the concentration of products. So this reaction, the rate of the reaction is actually minus delta R by delta T, because the reactant concentration is decreasing and the product concentration is increasing with the time. Then we have something called as average reaction rate. Which is the change in the concentration of reactants or products over a larger amount of time, over a large period of time. The time intervals are large here. Instantaneous reaction rates give the rate of reaction at that particular instant at that particular point of time, which is represented by d, letter d, r by dt. So if at all I am mentioning dr by dt or dp by dt in my equation, I am talking about instantaneous rates. And if I am mentioning delta r by delta t or delta p by delta t, I am talking about average reaction rates. We have, if we have a reaction, let's say A moles of A plus B moles of B is reacting to give us C moles of C plus D moles of D, then the rate of the reaction in terms of reactants is written as the concentration of A to the power A multiplied with the concentration of B to the power B. So these powers which are raised to the concentration can be the stoichiometric coefficient in a balanced reaction, or they can be experimentally determined. They are experimentally determined. These values are called the order. So A is the order of reaction with respect to A. B is the order of the reaction with respect to B. Overall order of the reaction is A plus B, which is generally represented by letter N. So this is the overall order of the reaction. So in case we have another reaction which such as AA plus BB plus CC gives some product, then the overall order of the reaction N is A plus B plus C. According to individual components, according to C the order is C, according to B or the order is B, and according to A the order is A. So this is the overall order of the reaction. So this is called the rate expression, that is the rate is expressed in terms of A and B. To remove the proportionality, I can introduce a constant where I can write the rate of the reaction is equal to K, small k, times A to the power of A and B to the power of B, where K is the rate constant. Yes. Now the order of the reaction can be 0, it can be any whole number 1, 2, 3, or it can be fraction also. It can be whole number and it can also be a fraction. And order of the reaction is determined experimentally. It's determined experimentally. Okay, hope you have understood order of the reaction. Next is units of rate constant. For depending on the order of the reaction, the unit of the rate constant K is different. Standard, which are generally asked in our exams, is 0 order, first order, pseudo first order, and sometimes they ask second order. But for first order, let's look into the units of the reaction for first order reaction. So in general, if I have A, B, B gives C, C plus D, D, then the rate expression is rate is equal to rate constant multiplied by A to the power of A and B to the power of B. Now if I want rate constant K, I just have to write K is equal to rate divided by A to the power of A and B to the power of B, where I can write this in general as rate divided by concentration of reactants to the power or n, where n is order of reaction. Overall order of the reaction. So for zero order reaction, n is equal to 0, which makes K is equal to rate divided by concentration to the power 0. This term, concentration to the power of 0, any term to the power of 0 becomes 1, which makes it K is equal to rate. So basically what it means is the unit of rate constant K is same as the rate of the reaction. And this is for a zero order. For a zero order reaction, the unit of K is same as the rate of the reaction. So what is the unit of rate? It is mole per liter second. So for zero order reaction, this is the unit. Sometimes this can be asked directly. You can see that in books it is written as mole liter to the power of -1 and second to the power of -1. This is the same. Okay, these both are the same. Let's move on to second order reaction. No, first order reaction, sorry. Where the value of n is equal to 1. For a first order reaction, we have K is equal to rate divided by concentration to the power 1. Now the rate is mole per liter seconds divided by concentration, which is mole per liter. This becomes mole per liter seconds multiplied by liter divided by mole. This gets cancelled, leaving us 1 divided by second. K has a unit 1 per second. It has a unit per second. So this is for a first order reaction. For a first order reaction, the unit of rate constant K is per second. Similarly, for second order reaction, K, N, the value of N is 2, K is equal to rate divided by concentration to the power 2, which is mole per liter second, which is the rate's unit, divided by concentration, which is mole per liter, whole to the power 2, whole to the power 2, which gives us mole per liter second multiplied by liter square divided by mole square, and mole and one of the moles get cancelled in the denominator, while liter in the denominator and in the numerator one of it will get cancelled, leaving us with liter divided by mole second. So the unit of rate constant K is liter per mole second. In books you'll find it written as mole to the power minus 1 liter second to the power minus 1. So this are the three different units which are there for first order, second order and third order reaction. For pseudo first order reaction, it is same as first order reaction, where the unit of K is per second. Further moving on is molecularity of a reaction. Molecularity of a reaction is the number of molecules that have to simultaneously collide for the reaction to occur. So if these are the minimum number of molecules that require to collide with each other for the reaction to occur, there are no zero molecular reactions. You need at least one single molecule for the reaction to occur. So order can be zero order, but molecularity can never be zero, and it is always a whole number. Molecularity of a reaction is always a whole number, it can't be a fraction. Order of the reaction can be a fraction. Remember this. Even this question can be framed in my MCQs as a direct question for you. We'll just look into some examples so that we get some clarity. Let's look into unimolecular reaction. Example which has been mentioned in NCERT, NH4NO2, which is ammonium nitrite, is decomposing into nitrogen and water. This is a unimolecular reaction. There is only one molecule. This molecule, presence of this molecule is sufficient for the reaction to occur, a single molecule. This molecule needs to have certain amount of energy within itself for the reaction to occur. That minimum amount of energy is called activation energy. If that minimum amount of energy is not present in the molecule, then the reaction will not occur. Example for bimolecular reaction. Bimolecular reaction, we have two molecules of HI, that is hydrogen iodide. Two molecules of it is required. Two hydrogen iodide molecules are required to collide to form an intermediate compound which is attached to each other for a very small time, for a very limited period of time, very small time it is attached to each other, and this immediately decomposes. This intermediate molecule compound which is formed, this immediately decomposes into the products, that is hydrogen and iodine. So 2HI gives hydrogen H2 plus I2. Okay, so this is an example for bimolecular reaction. Now let's look into a trimolecular reaction. Example that's given is 2NO plus O2 gives 2NO2. So in this case there are two molecules of NO which is colliding with one molecule of oxygen. Now this collision should happen simultaneously. These three molecules need to simultaneously collide, all the three at once, for the reaction to occur. If this collision does not happen simultaneously, if only NO is colliding, if two NO molecules are colliding, or one NO molecule is colliding with another oxygen molecule, the reaction would not occur. We would not get a reaction. So the minimum number of molecules required for the reaction to go forward is the molecularity of the reaction. Hope you have understood this. Briefly I have explained. I am not going into detail of any of these explanations. Next, the rate equations. Let's see for zero order reaction. I'm not doing the derivation over here. I'll do the derivation separately in another video. For the purpose of solving the NEET IIT-JEE CET questions, how much ever data I require right now, I'm just taking those. I am assuming that you have read these particular derivations in your book for your board exams, obviously. So let's not spend too much time on those, but I will do the derivation for these reactions, these rate equations, in a separate video. Let's go for zero order first. For a zero order reaction, let's see a reaction such as reactants gives products. The rate of the reaction is equal to the change in the concentration of reactants with time dt, which is nothing but, according to the rate expression, K times R. For a zero order reaction, r to the power 0. So this is the first zero order reaction. Now this tends to 1 because anything to the power of 0 is equal to 1, so it will be k into 1. So the rate becomes k. That is minus dr by dt is equal to k, integrating the above expression. Now there are two methods in which this can be integrated. Either you can use the limits and directly do it, or you can use the support of integration constant. In any case, after finishing the integration, we get the value R concentration is equal to negative kT plus R naught. For getting the value of K rate expression, I have the equation K is equal to R naught minus R divided by T, an expression which we use for our problems, which has to be remembered by us. So this is for zero order reaction. This expression can be used only if the reaction has been mentioned to be of zero order. Further, another expression in the same where which we use in our problems is for half-life of zero order reaction. So what is half-life? Basically, the half-life is the time taken for the concentration R naught to decrease to R naught divided by 2. So half of whatever the initial concentration is, the time taken for this particular time, for this particular concentration to decrease to half of it, is the half-life. And the half-life for zero order reaction T half is equal to R naught divided by 2t. Derivation which is very easy to be, 2k. Yes, even this should be remembered by the students so that the calculation can be done faster. You don't spend too much time. Then first order reaction. For first order reaction, we have the rate of the reaction, which is minus dr by dt, which is equal to k times reaction to the power 1. So first order reaction where the order of the reaction is 1. After integration, above expression, we get k is equal to 1 divided by t, natural logarithm of r naught divided by r. And in terms of log base 10, the expression is written as 2.303 divided by t log of r naught by r. How? If anyone wants to know it, if you know, this is a very standard conversion from natural logarithm to logarithm, that is to multiply by 2.303. If anyone has a doubt on it and if you want to know how it is done, you can mention in the comments. I will do a separate video for that for you guys. Half-life. T half. That is when the concentration of initial concentration has decreased to half. T half for first order reaction is 0.693 divided by K. This is also straightforward. I hope you remember the derivation for this segment. For a pseudo first order reaction, we have a pseudo first order reaction. The reaction rate is dependent only on one of the reactants, and the dependency is of first order. The other reactants, it doesn't matter, because the concentration of the other reactant is taken at very excess and high concentrations. So if we have A plus B, the reaction should be dependent both on A and B, but if concentration of B is very high, then the reaction behaves as though it is not dependent on B and it is only dependent on the term A, the concentration of A. In general, for this, we can write the rate of the reaction as K times A and B, but since the concentration of B is excess, we can generalize this expression as K dash, which is K multiplied with B, which is going to be a constant for this reaction, because this is maintained at a high concentration and it is going to be a constant. It's not going to vary with the reaction, it's not going to matter much, it's not going to vary. The variation in B is not going to matter much. Only the variation in A is going to matter for the rate of for determining the rate of the reaction. So we can write the rate of the reaction is K dash times A, that is, it is dependent only on the A, and the order of the reaction is 1. With respect to A, it is 1. In this case, if the order of the reaction with respect to A is anything apart from 1, that particular order of the reaction should be considered. Okay, so in this case I am considering, according to the A, the order of the reaction is 1, so it is a pseudo first order reaction. And I have my K dash is equal to 2.303 divided by T log of initial concentration of A divided by final concentration of A. This is not A naught, sorry for the mistake. And half time T half is equal to 0.693 divided by K dash. Now coming to one final concept in this particular chapter, that is relating the activation energy with the rate constant, that is the Arrhenius equation. Arrhenius equation, standard equation K is equal to Arrhenius constant multiplied by exponent of minus EA divided by RT, where K is the rate constant, at temperature T, capital T, because this temperature should be mentioned in Kelvin. The unit of this temperature is Kelvin. EA is the activation energy. What is activation energy? Activation energy is the minimum amount of energy that should be present in the molecule. This amount of energy should be present in the molecules for the reaction to occur. Below this, even if the molecules collide, the reaction will not occur. So this minimum amount of energy should be there in the molecules which are colliding for the reaction to occur. That is the activation energy. R is the gas constant. That has the value 8.314 joule mole per liter Kelvin, and T is absolute temperature. Temperature in kelvins. Now we have another expression where the rate of the reaction is equal to ZAB e to the power of minus EA divided by RT. Equation which is very similar to Arrhenius equation. Here ZAB is the number of collisions between A and B. A refinement in this particular equation is written as the rate is equal to P ZAB e to the power of minus EA divided by RT, where P is steric factor. Let's understand what this actually is. If A and B are colliding, if molecule A and molecule B is colliding, let's consider B to be an enzyme. It is not a small molecule, it is a large molecule, it is an enzyme, and all the enzymes will have something called as an active site. If the molecule B, the substrate, is colliding with this particular activation site, at this particular site, only these collisions between the active site of the molecule and molecule A, only these collisions which are happening at the active site is going to create a product. If any other collision, if the collision happens in any other orientation, the active site is here, and the molecule B is colliding with A, in any other position, it's not going to give product for us, because this is not an effective collision. Effective collision is that which can create a product, and effective collisions is very important when it comes to large molecules, biomolecules especially. In terms of enzymes, the collision only if the substrate is colliding at the active site of the enzyme, the product is going to form. So it is a huge matter. It matters a lot when it comes to enzymes, large molecules. Only properly oriented collision is going to give reaction. So that is, how many effective collisions are there? Collisions divided by total collisions. From the total collisions, how many effective collisions are going to occur? That is the P multiplied with the number of collisions between E and B into e to the power of a divided by rt. Okay. Coming to one last formula which is important, which you have to remember, is for two different temperatures, T1 and T2, the rate constants will be K1 and K2. K1 and K2, and we can write log of K2 divided by K1 is equal to EA divided by 2.303 multiplied by R T2 minus T1 divided by T1 T2. Another important equation which can help you find out rate constant at two different temperatures. So here are a few important equations which I have discussed with you, which can be used for solving our problems related to this particular chapter. I have not gone into any detail in this, assuming that you have read in detail these particular equations and their derivations in your board exam. I have mentioned those equations which are important for you to remember, so that we can go ahead with solving the problems in our exams. Yes. Now, thank you. I hope I have got at least some information. Thank you. I hope you have understood, and we'll move on in our next video with solving the problems. Thank you again.